Oh, not this one. It's a spoiler. Sorry. Hello, everybody. My name is Franz Lefrère from STMicroelectronics, and I would like to talk to you about secure boot, how to protect it, what is a secure boot, and the isolation mechanism. I don't know if you are familiar with security, but I would like to address the three. And if you don't know anything about security, I hope you will understand this presentation. First, one question. Do you think security is important for your product? Do you need security? Yes, no. Frankly speaking, I'm a technical supporter, and I see many products that go on the market with the debugging link open, without any security. Okay, this is a joke. This never happened. But this kind of attack is possible. And what is the impact for your company? Unicorn on all the devices. It makes you smile, or not, but it will not make smile your company. Your business is completely destroyed. Nobody will believe you after this. What about my personal data as I share with you? What is, no, I can't use this device anymore. I will not accept this. And it's why security is a must in your product. Even if we know that we have regulation that's coming, CRA and RED, that force you to use security, but just have this mindset. I have to take care about security of my product. It's to protect my brand, all my money, and all what represents my company. So I will start by defining what is a secure boot. What is the purpose of this piece of software? Then I will talk about isolation. Because in security, we often say, use isolation to improve the security level. What is isolation? Many people don't know exactly what is this, so I will try to explain it in a simple word. Finally, I will talk to you about high memory protection. This mechanism we've got in our device, STM32, how to protect the secure boot. And finally, some takeaways. So let's start with the purpose of the secure boot. Your product, based with the MCU, embedded some firmware, where the attackers or the hackers will come to try to break in your device. This is what we call the surface of attack, where the burglar will try to come and to introduce inside the device. It will be all the interfaces. You could have the debugging link, local one, the USB, or over the internet if your object is an IoT connected to the net. The hacker will try to inject unicorn there and put this in your device. How we will mitigate this threat? And the first brick that we will use for that is a secure boot. What is a secure boot? It's a piece of software, and it has two properties: immutability and unique boot entry. Do you know what does it mean? Immutability, that means can't be modified in any manner. Nobody can modify it. It's a ROM code. If it's not ROM, we will make it ROM. Read-only memory, can't be modified. Unique boot entry, you are sure to always boot on this code. A code that you can't modify in any manners. You always start on this. This is what we call a root of trust, what you started to believe. Based on this, we can create the security in our device. The role of this firmware, it will be to check the integrity and the authenticity of the firmware. Two different words are not exactly the same things. Integrity, you ensure nobody has modified this firmware. If I try to write something in this firmware, integrity will be break. If I can detect it, I will not launch it. I will not display the unicorn on the screen. Authenticity, to ensure it was your firmware, the firmware that is produced in your company, and not from another company, a concurrent, or a hacker. So with those two, you are sure about the firmware and you will launch it. Often, the other role of the secure boot will be to handle the secure firmware update. How I can update this firmware securely. It will be this piece of software that detects that there is a new firmware available. It will check integrity, authenticity of this new firmware, and install it if it's needed or if it's possible. Other role of this firmware update, we can also guarantee the confidentiality of this firmware. That means we will encrypt this one. To do this kind of things, we are using cryptography. For the cryptography, you are using keys. For the integrity and the authenticity, asymmetric cryptography, and we just use a public key to check the integrity and the authenticity. This is a signature check. Okay for you? And we could also have a symmetric key for the confidentiality. If we send the firmware encrypted, we need to decrypt it. And usually, we are using symmetric cryptography for this task. So this is exactly the root of trust. But we have to protect these parts, because this is the more valuable things. So we should ensure that this is not exposed to the firmware. And it's where we say using isolation will improve the security level of your device. So the question is, what is isolation? What do you mean by isolation? So to explain isolation, I will compare my system to a house. House have door, windows, everything inside. In my house, not everything is valuable. I've got old furniture. If a burglar enters by the door, try to steal my furniture, I don't care, it's an old one. But all my bank paper, my money, my TV, I like my TV, it's a big one. I want to protect them. So I have to think about it. So first thing in a house, I always close the door. Who don't close the door of his house when you leave it? Nobody here. For the product, it's the same thing. You will have at least to close the door, the debugging link. And in my house, I will build just one room, which will be one piece. One room, which only one door. No windows, just one door. And I will put what is valuable in this location. Okay? So now I've got these architectures. And when I work in this area, I'm close my windows. I want to be sure that no burglar will come when I'm working there, because it was really important for me. I don't want anybody to enter in this house. When I finish to work with all this stuff, I close the door and I live in my house and I reopen the windows. I think you understand clearly this analogy. It's like a house and I create a dedicated room. This is isolation. If I come back to microcontroller world, you can have the equivalence. Debugging is like the door. At least, if you don't do security at all, at least you have to deactivate the debugging link on your device. Or it's like a door open. Hacker can connect in any way and do whatever he wants. He has access to all the resources. The interfaces we have outside, the windows, could be a USB link or the internet connection. In a house, you need to have some light. You can't live with all the windows closed. Connected devices need to communicate with outside in such a way. And it's where we have to control them. So we'll come back to the high memory protection, which is an isolation mechanism. So this secure area will be the equivalent where we will put our secure boot somehow. So HDP, which is the high memory protection, is a mechanism that we can define a location in the flash that will be protected. When we are booting, everything is available. But we deactivated completely the debugging link. We have no USB access and no deactivated also the internet connection. That means we have closed the door and the window of our house. We can work with the secure boot. So the secure boot starts. It will check the integrity, the authenticity of the firmware, and then we'll launch it. But when you will launch it, you will write in a register and make disappear all this region. As we have closed the door of the secure room, here we remove any access to this portion of firmware. The secure boot and all the keys are fully isolated from the rest. Then I launch the execution of my firmware that will reopen connection because it was a functionality that is needed. Okay? But now if a burglar managed to enter with such interfaces, he can try to modify the firmware, but it will be detected by the secure boot at the next boot. But it can't access at all the secure boot resources, the code and the keys. So this region can't be accessed until the next reset. At the next reset, everything will be deactivated again, and my secure boot will start. It's the unique boot entry, and it's immutable. So this is a basic one. On our platform, we have extended this functionality, extended to a two-stage bootloader. You remember the two properties of the secure boot? There is immutability. That means if you have a bug in this portion of code, what's happened? You have to live with it. If it's an important bug, a security hole, it's there. You can't do anything. So one rule when we create a secure boot is to put it as tiny as possible, with less bug possible. That means less functionality. Okay? For example, if you have to handle an external memory, I will not do this in the first stage bootloader. Okay? I will create a second stage bootloader. That means a second secure boot. The first secure boot will authenticate and check the integrity of the second stage bootloader. And in this second stage bootloader, I will have a secure boot, but with extended functionality. Handling of external memory, whatever you want. Maybe you switch on another GPIO or something like that. So the purpose of a two-stage bootloader, you have this one that can't be updated, but this one can. And this one is secure. Okay? So the role of the secure boot level 1 will be to check the integrity of the authenticity of the second stage bootloader. That will check the integrity and the authenticity of the final firmware. You have your chain of boots. On the HDP, we can now define two regions. And you can imagine what happened. Associated with them, they have some key storage. And we can make disappear each portion. We started, first stage bootloader, check integrity, authenticity, then make disappear from the system. There is an isolation between the two levels of the secure boot. This one is updatable, securely, of course. And then it will check integrity and authenticity of the firmware. So as you can see, two-stage bootloader, and we have this extension of the high memory protect to the both. Nice features. If you have attended to the previous presentation from my colleague, you already know about debug authentication. And here also, we have extended this high memory protect to the return from the field analysis. I told you that I closed the door of my house. But if I've got a bug, I would like to investigate. I don't on the field, there is an issue with my device, it's completely stuck. I don't know why. No way to communicate with it. I would like to reopen securely the debugging link. This is possible. But if I reopen, I will have access to everything. So what we have done, we have, I will say, imbrick the debugging capabilities reopening to the level where you are in the boot chain. So what happened? In my secure room, I can create a license to reopen the debugging link just for level 1. That means for level 1 and upper, because when level 1 is executed, you have access to any resources. This license is only for the advanced debugger, the guys who can have access to everything without compromise the security. If I want, I can do a license which only allows the debug when you are in level 2. That means you can't access at all this portion of flash. That means you can restrict the opening of the door of your house depending on the activities that is executing currently in your device. And finally, we can use a level 3. And in such a way, with this license, you can just reopen when you're executing the final firmware. That means I can give to a team the capability to investigate the application without, I would say, reveal all my secrets that I've got in my boot chain. So now I will sum up the advantages and the drawback of this mechanism that we've got on our products. One advantage is it's available on many families. From the C0, which is a really tiny device, up to H7S, RS, H5, U5, so ultra-low power family, and also connectivity. So really simple mechanism, available on many different families, which is from the high-perf, entry-level, but also wireless. It's quite simple. The configuration of this area It just defines statically for the first stage bootloader. Statically, that means you program some what we call option byte, a portion of the flash that remains to a boot. That means you can reset. This configuration is always set. This is for the first stage bootloader. For the second one, it will be the first one that will define it in a register. That means in a register, it say for this range of address, it was the next level. And then to increment this HDP level, to close a region, you just have to write in a register. Writing in a register will increment a monotonic counters, which reflects the level of HDP. 0, everything is open. 1, I'm close the first stage. 2, I'm close the second stage. Then I'm executing my application. So from implementation point of view, it's quite simple. Main drawback, when you close this region, it's closed until the next reset. So imagine you want to use those cryptographic keys to do something, to do encryption or things like that in this location. You can't do it. Once you are in the firmware, you can't access those resources. That means this isolation mechanism doesn't allow you to get some security services. So that means you will need to combine this, if you need this functionality, to other isolation mechanisms. So the other isolation mechanisms that exist, we've got firewall on the L4 family. Memory protection unit, I'm nearly sure you already know this. It's a Cortex features, so ARM Cortex features. And we have extended it to all the platform. Trust zone, that have been told by my colleague before, which allow to define a portion secure, a portion non-secure on some security services. And the resource isolation framework, which is more in the world of the MPU, but also on our new product, the STM32N6, which is really an extension of the trust zone to all the peripheral inside the platform. So a lot of information. Security is not a simple topic. You've got a lot of different mechanisms you have to combine together to build your security. So often the question is where I could start from. In ST, we can provide for you some secure hardware. That means the HDP mechanism is, for example, hardware that is provided to you. You decided to use it and do it by yourself. You know how to create secure boot. If you don't know how to create a secure boot, we also provide secure boot for many of our platforms. I don't say all, because the oldest one, frankly speaking, we don't have secure boot at all for the very first family. But as soon as we have some secure hardware, we have the capability to provide you secure boot code example or ROM secure boot. Security services, on some platform where you've got trust zone, or you have the capability to have some secure services. That means your application is running, but can access some secure services thanks to a specific API. It will mainly rely on trust zone isolation. But here also, we have a ready-to-use implementation of this. An open source version, which name is TFM, which is the ARM standard also, but also a proprietary answer, which named Secure Manager, which allows to take care about all this stuff without any implementation. We deliver it as a library, or binary, sorry. You will install it on your platform, and all this stuff will be handled for you. And finally, your application. Here you will have to work. We can't do it for you, for sure, but we can help you for this. Okay, you can't read all this stuff. I put it on purpose. It's just to show you that over all the family, MPU, high performance, mainstream, ultra low power or wireless, for each one we have different security functionality available. Everything is not available on all the platforms. For example, a secure firmware installation in industry where it's not secure, it's not available on all our devices. But all our devices have their own, I will say, potential hardware bricks, software bricks, and we have just a mapping of all this stuff. That means one of the criteria when you selected a device will be also which level of security you want to achieve. If we have the functionality for this family, and it's important to take account the security at the beginning of your product design. Which level of security is needed for this device? Where we can help you, in fact, we have defined a whole framework about security. The name is STM32 Trust, and this is the web page of this one. We have defined 12 security functions. Secure boot, secure firmware install, secure storage, where we can secure keys, isolation, abnormal situation, crypto engine, how we can accelerate cryptography, audit and log, how we can track issue or what happened on the target. Identification, authentication, attestation is more for IoT, or to ensure there is no cloning of your device. Silicon lifecycle, how can I close my device, reopen it when you return on the field, and such kind of things. Software protection IP, how I can ensure the protection of a portion of my firmware, but not the complete one, because this one is coming from a third party. Secure manufacturing, how can I program, inject all my code and also my keys in an unsecure environment without leakage of those secrets. And application lifecycle. I don't say we can address all those, but we have listed them, and we propose solutions that we can address with our mechanism or how you can address in your product. So visit this, and it will help you to understand what are the different capabilities that you can achieve on the level of the degree of resistance you can achieve. And now we are ready to discuss your project. So here, right now, or after on the booth, do not hesitate to come and visit us. We'll be happy. Do you have any question about this presentation, the security, isolation, and memory protect, or whatever you want to talk about? Anyone? Who will start? Just one question, please. Okay? Nobody? Oh, sorry, I was not seeing you.
Hi, thanks for the presentation. You spoke a little bit on the hardware protection,
Yes.
security. Please, can you maybe just talk a little bit, maybe for the few minutes we have, on how you actually achieve security on the hardware level with absolutely no software?
Okay. So when I'm talking about security at the hardware level, it's those hardware mechanisms that are inside the silicon. But to go further, when you are using cryptography, like crypto accelerators, we are resistant also to external attack. That means if you have attacks that are using side channel attack, not through the debugging link and such kind of things, okay? We have accelerators which are resistant to this kind of attack. So side channel attack is, you know, when you're spying some external signal to manage to recover a secret that is inside. So now we have on some specific device those accelerators which are resistant to those ones. Does it answer? Yeah? Any other question? So everything was so clear. I'm happy with that. So do not hesitate to come back to the booth. I really like to talk about security. You have seen my colleague Jocelyn. We also have a dedicated booth about CRA, this regulation that's coming. Think about it. If you don't take care about security today, you will have to if you want to sell product in Europe. So thank you, everybody, and have a nice embedded world.